Primary interest as climate scientists is the development of very high resolution records. Many of the climate records we have a resolution of thousands of years to tens of thousands of years or even millions of years. Now, a lot has happened in the last million years that we wouldn't know anything about if we only had one number to describe the last million years. Same goes if we had one number for the last 10,000 years, or one number for the last 1,000 years, or even a number for the last 100 years. Now we're getting somewhere, for sure, but that's still fairly low resolution. Ultimately, it'd be great to have chemical records that are on a minute-by-minute basis back in time. That's not going to happen. It's too expensive. It's technically difficult to impossible. So we work with what we've got. We can do much better than we've done in the past, however. So here's an example from some work we did in Ireland. This is a cross-section of what's called a marl bench. This is calcium carbonate that's produced by the algae that live here in the shallow water. This algae produces little grains of calcite that fall off the algae and accumulate, forming a white sediment. You've seen this if you've been to carbonate-producing lakes in Western Canada. Kananaskis has a couple of them. There's a bunch of them in British Columbia. There are a few in Manitoba. There's a couple in Saskatchewan. They're generally bright blue water. Little Limestone Lake in Manitoba is a spectacular example, for central Canada anyway, of a marl lake. So this is a marl bench at Patterson Flats. Didn't know it was called Patterson Flats until I'd been there maybe 4 or 5 times working and talked to a local, and that's what they call it. So it's the swampy area here at the end of the lake that's called Patterson Flats. We cored this area to get this core in 2002, and the radiocarbon dating at the top indicated that this mud was about 7,000 years old. So we missed the last 7,000 years in taking this core at this location. So we go to plan B, come back the next year, and we're going to core out in the lake so that we get to modern carbonate mud. A couple of shots of the coring operation. This is putting our gear together, flatten down some of the reeds to have some space to work. It's a fairly muddy operation in many cases, particularly if it's raining. This is taking a core from the side of the lake and coming back the next year and taking a core in the lake where we walked out up to the depth at which my wallet was going to get wet. I put my wallet in my shirt pocket because I forgot about it. So we were limited by that in this particular coring episode. We got back to the lab with the core. You can see being recovered here. And we found out that the top of the core was 7,000 years old. So we topped out at 7,000 years in both the in-lake core and the side of the lake core. That's when the carbonate stopped being produced, and there's a reason for that again we'll get into a little bit later in the course. So we can take this type of sediment from these lakes, and being calcium carbonate, we can get carbon isotope numbers from that sediment, from the calcium carbonate, and we can get oxygen isotope values from that calcium carbonate. In this case, we're looking at the carbon. What does the carbon mean? The carbon isotope values of a lake mean? And what we determined was it means that precipitation is going up and down. And this is a bit of an odd thing to conceptualize, that water is recording the amount of water available to that body of water. That is to say, the wetter the region, the lower the carbon isotope value. That's because plants like moisture. Plants aren't stressed when there's sufficient moisture, so they respond by having a lower carbon isotope value when there's lots of rain. This means we can use the carbon isotope values of a lake as sort of a rain indicator, which again might seem a little odd at first. Hopefully this will make more sense when we get into the isotope business a little bit more later in the course. Here is a plot from Cayuga Lake, also in central New York, located not too far from that last record you saw, where we can look at a 13,000 year deposit of calcium carbonate material. So we go from the modern, in this case it was 1969, when a marina was put in, and that's the end of the carbonate record. That's another story. So 1969 is up here, and then we go back to about 13,100 years ago. So you can see from 13,000 years ago to about 6,000 years ago, it was more humid than today. So these would be humid June, July, and August. We get into a dry period from around 6,000 years ago to about 1,600 years ago or so, maybe 1,500 years ago. And then it gets wet again. We believe it was a very dry spell here from about 2,400 years ago to about 1,500 years ago, in which the carbonate sediment dissolved. The lake levels dropped, the carbonate was exposed, and it just went away, it dissolved. We can get a long-term record of precipitation and humidity from the carbon values here, where the oxygen 18, oxygen 16 record here in white shows us fluctuations in the source of precipitation. We can see that we go from, in some cases, very low periods of precipitation, summer precipitation, to relatively high summer precipitation. This is confused a bit because these lakes are fed to a large degree by what's called lake effect snow. And we'll get into what that means a little later in the course as well. But lake effect snow produces about 74% of this lake's water budget any given year. So that messes up our record of humidity and summer precipitation a bit, but that's okay because we get it from carbon. What this represents early on, these wild fluctuations, are probably the appearance and disappearance of very, very large lakes in central North America. These are the Laurentian Great Lakes today, Lake Erie, Ontario, Michigan, Superior, and what's the other one? Huron. Those are the 5 Laurentian Great Lakes today. In the past, they were much bigger, and they drained very rapidly at certain times. And those certain times of rapid drainage are indicated by these wild swings in the isotope value. Again, we'll get back into that in a bit. So one of these drainage episodes in which the large lakes located out here in northern Minnesota, mostly Manitoba, a little bit in North Dakota, a little bit in southeastern Saskatchewan, drained catastrophically in about 3 weeks. So it's like dumping the modern 5 Great Lakes into the North Atlantic in 3 weeks. That's a lot of water. It's fresh water. It's low density, so it slides over the North Atlantic like oil on vinegar, and it stays there. And that shuts down that thermohaline circulation that we saw earlier that is influenced by the precipitation of Panama. So when the lakes go away, we have a contracted circumpolar vortex or jet stream. When the lakes are refilled, we see a shift in this circumpolar vortex to represent the appearance of the lake, the refilling of the lake, that big cold spot here in central North America is going to have an influence on atmospheric circulation both upstream and downstream from that location. And our sample location here is the Finger Lakes, located under this dot. So we're able to use the record here, coupled with our record of the lakes filling and draining here, to produce a record of the general position of the jet stream in the past. In this case, we have the modern, we have the Younger Dryas Cold period from 12,600 years ago to around 11,006. The post-Younger Dryas starts around 10.3, and we can see where we transition into basically the modern world, modern circulation patterns at this time, at the end of this cold period. There's a brief resurgence of trouble at around 8,200, 8,300 years ago. Again, we'll get back to that a little later in the course. So global change on short time scales is important to evaluate because evidence for global warming can be derived from these types of studies. You have a high enough resolution record, you can look at the types of time periods that are going to be of great interest to us in the near future. The next few decades are going to be most interesting to us, people alive today. Of course, people that come along in a few decades are going to be more interested in what's happening a few decades further down the road. So global warming is perhaps the most important and, to a large degree, the most controversial issue that faces people today. Why is it important? Well, it affects everything. Climate affects the living and the non-living on Earth. When it's too hot, plants die, animals die, people die. When it's too cold, plants die, animals die, people die. The weathering rate of rocks, the creation of soil, all of these things are tied directly to temperature and precipitation. So as climate changes, it gets warmer, colder, wetter, drier, the animals and plants present in any given region are going to change. The precipitation amount will change the weathering rates. The temperature will change the weathering rates. The soil health and productivity will change. Again, everything is influenced by climate. Not everyone believes that global warming has started. So we're going to need to look at the evidence for and the evidence against global warming if we want to truly understand what it is and its implications. Now, there are a whole bunch of studies done by a number of different groups. We'll talk about these a bit more down the road, but just for a starter here, we'll start out with the topic of climate change. Now, this could be temperature rise, sea level rise, precipitation change, which results in droughts and floods. We can go two ways with this. We can adapt. We can change our systems to embrace these new changes, or at least survive these new changes. That will involve changing our food and water resources. We have to prepare for changing precipitation. We have to prepare for changing food availability. Hopefully we'll have a better understanding of ecosystems and biodiversity so that we can better prepare ecosystems for these changes. Human settlements can adapt to these changes, or they can change themselves to prevent having to adapt to these changes. And of course, human health is going to be a great concern to humans, predominantly. That's going to fluctuate. Now, we see trouble spots around the world throughout human history. It's often tied to resources, the haves and the have-nots. The haves often want more. The have-nots maybe can't defend what little they do have, and it's taken away. Or the have-nots rise up and take from the haves. This is, again, human history going back hundreds of thousands of years. So this is going to lead to different socioeconomic development paths. So we can see economic growth that may be tied to changing patterns in climate and ecosystems. We can see changes in technology. We see this now. We are transitioning to wind power and solar power. Changes in population. Unfortunately, the population is still going up. That's not helping anybody other than the new members of the population. And we'll see changes in government, how people respond to these changes, whether they be good or bad changes. And this brings us to mitigation. We can maybe stop doing the things that are causing the problem in the first place. That seems like an easy solution, except we like the things that are causing the problems. We like cheap gasoline. We like cheap natural gas for heating our houses, apartments, condos, townhomes, farms, etc. So it's hard to take that away. Once people have something, it's hard to get it out of their hands. In the cases where we can get it out of their hands, we can reduce our effects, our influence, the negative influence, by reducing greenhouse gases, for example. Switch from burning coal to producing solar panels, one example, or wind power in place of coal power. We can reduce the amount of aerosols we put in the atmosphere, which results in a clearer atmosphere. That brings one problem in that if the atmosphere becomes clearer, then we may trap more heat at or near the Earth's surface, making conditions worse, warming things up. And we actually saw that in the 1950s, 60s, and 70s with the rapid rise in pollution followed by the decrease in pollution with the Clean Air and Water Act of the United States, reducing coal-powered plant emissions of sulfur dioxide. So we cleaned up the atmosphere in the 70s, and we made it clear, and it suddenly started getting warmer. So by cleaning things up, we may actually accelerate global warming in that instance. So we can influence our emissions and concentrations of things we put into the air, the water, the ground, etc. And that will hopefully mitigate some of this climate change. If we prevent this climate change from happening, then we don't need to worry about a lot of these other things. What do we know is true about climate change and about global warming? Well, we know for sure that we're adding CO2 to the atmosphere, carbon dioxide. It has natural sources and it has anthropogenic sources, human-made sources or human-induced sources. Keeling, a scientist who started this collection process back in the 50s, was quick to observe that CO2 concentrations were going up fairly steady, not at a steady rate, they're actually increasing, but they are going up from year to year. You see some fluctuations here on 6-month time intervals that you should think about for a couple minutes after you turn this off. What causes this increase in CO2 part of the year and a decrease in CO2 the rest of the year? When in general CO2 amounts, the percentage or partial pressure is increasing through time. So we're now at about, I think, 420 parts per million. So even though this chart is only 10 years old or so, it's way out of date already. Again, we're up to about 420 off the scale here somewhere. Okay, so when talking about the carbon cycle, we have to think about how rapidly carbon is put into the atmosphere and how rapidly it's taken out of the atmosphere. So here we have vegetation. You can think of this as the earth breathing. It inhales CO2, produces plant material, sugars, leaves, stems, twigs, wood. CO2 is removed. It's stored here in that form, the form of a tree. When that tree dies, that tree decays, CO2 is generated, and that CO2 goes back into the atmosphere. In some instances, like we're all familiar with here in Western Canada, forest fires burn down very large amounts of this biomass. This part of the biosphere is being converted into CO2, which then goes back into the atmosphere, again, rapidly. Some of this carbon dioxide that's turned into plant material gets buried in the soil, becomes part of that soil. Eventually it's going to break down in the soil and generate methane and CO2, and that's going to go back into the atmosphere. Now we can put that on steroids, so to speak, and go into factory mode here. We're now taking fossil fuels, buried organic matter that was taken out of the atmosphere just like this, but hundreds of millions of years ago in some cases. We suck that carbon up into our factories, we burn it, and we turn it into CO2, which goes into the atmosphere. So this is taking biomass that was stored over many, many millions, even hundreds of millions of years, and injecting it right back in the atmosphere instantaneously, at least for our purposes. Some of this CO2 goes into the ocean, dissolves into seawater. It's exchanged from surface water back and forth. It's not really at equilibrium, but close to it. Some of this CO2 is used by phytoplankton. This phytoplankton, these little microscopic plants in the ocean, are eaten by microscopic animals, zooplankton. These in turn are eaten by larger animals. And when those large animals die, they may drop to the floor of the ocean and break down, again, releasing CO2 that's eventually going to work its way back into the atmosphere. Conversely, these little critters can sink to the bottom of the ocean, become incorporated in the sediment, and ultimately be compressed and heated and converted into oil and gas, just like we see here. So we are removing some CO2 from the atmosphere today and converting it into sediment organic matter in the deep sea where it tends to remain. For our purposes, that's good, but it's not happening nearly fast enough to replace what's being pumped out of the ground and burned over here. Now, when we look at carbon dioxide concentrations, Keeling's been measuring that in Hawaii since the 1950s. You can see that here. Prior to the 1950s, we have to look for samples from other locations. One of the other locations are the little bubbles of air that are trapped in glaciers. So we can go to an ice sheet, remove a core of ice from that ice sheet, extract the bubbles from that core, and we get a CO2 concentration going back in time. In some rare instances, we have glass spheres that were sealed by scientists hundreds of years ago. For some experiment, we can break those open very carefully and extract the atmosphere from those vessels and get a CO2 concentration for that as well. But that's only going to be a handful of these numbers here. Nitrous oxide we can also get from measuring today directly or looking at ice cores back in time. Methane, same thing. Sulfate aerosols, we can look for them in ice. And again, all of these are rising rapidly, and all of these rapid rises are related to human activity. It's all anthropogenic forcing. So, CO2 in the atmosphere and annual emissions of CO2, we can see here the CO2 concentration, parts per million in the atmosphere, this purple line, superimposed upon this blue line, which represents billions of tons of CO2 generated by human activity. So we can see that it becomes very closely coupled in the 1960s, but a pretty good match prior to that as well, going back to the beginning of the Industrial Revolution back in the 1700s. So there's a good correspondence between the amount of CO2 in the atmosphere and the amount of CO2 we're putting in the atmosphere. Now people say, well, volcanoes erupt and that's a lot of CO2. Well, it is, but it's a tiny, tiny amount compared to what humans are doing. A very, very tiny amount in comparison. Looking back 800,000 years or so from ice core records, we can see that CO2 rises and falls over this 800,000 year record. This was without the influence of humans. Humans didn't really begin to damage the environment in a major way until about 2,000 years ago or so. And then in a really, really major way about 200 years ago. So what we see here is a decoupling of the natural system as we move into the modern world where humans have taken over this process and added to it considerably. So again, this is from 2014. CO2 is about 400 ppm. Now in 2020, it's up here around 420 or so. Let's say we all become good people, really good people, and we cut off the production of greenhouse gases. It's all going to get better, right? No, it's not. In fact, it's going to take a while. If we start to turn down the amount of CO2 produced in the next 100 years or so, we get a hold of ourselves. We turn down the production of CO2 here. What we're going to see is the temperature is going to continue to rise for several hundred years, and then that's going to trail off for a couple hundred years until we get out to about 1,000 years from now. Even if we do very, very good things right now, it's going to take about 1,000 years for the temperature to stabilize, to settle down. When we look at sea level rise, the sea level is going to continue to go up as the temperature increases, and sea level is going to go up because ice is melting, which you can see here. Our glaciers and ice sheets are going to melt, and that adds water to the ocean, which causes sea level to rise. But here, this is the sea level rise caused by thermal expansion. Just heating up that much water takes up more space, so the ocean gets fuller because it's warmer. Again, we turn off CO2 right now, and in a couple hundred years, the CO2 level in the atmosphere is going to stabilize and return to probably, we would hope, its normal fluctuation for the next glacial interglacial cycle. When we look at models of temperature change, we have temperature change on this axis relative to the 1850 to 1900 temperature. You always have to compare your temperature to something. You can't say it's warmer today. Like warmer than what? Warmer than it was yesterday, or warmer than it was 1,000 years ago, or 1,000,000 years ago. You have to specify warmer than what. So in this case, it's warmer than the period of 1850 to 1900. We have human-induced temperature change in this kind of grungy, orangey color here. We have the total forced temperature change here in red, we have the observational range. This is what we measure, the temperature variability we measure. So this is a moderated line, or a moving average, you might call it. And then we have superimposed upon that surface air temperature. This is taken from lots of different stations. This brings us back to that thing on aerosols I mentioned a few minutes ago. During the 60s, the late 50s to mid 60s, 70s, we had a recovery of the world's economy after World War II and the Korean War, and this led to a dramatic increase in production. This production required power. This power was supplied by coal power plants that were putting lots of aerosols in the atmosphere. These aerosols are like a shield or force field that keeps radiation away. So when we're putting lots of sulfur dioxide in the atmosphere, the temperatures actually go down at the Earth's surface. So we see that here. This was a big mystery for a while. People didn't know why temperature was going down, other than maybe the ice age is coming. Subsequently, in spite of doing a lot of bad things, Richard Nixon was responsible for the Clean Air and Water Act that forced companies to install electrostatic precipitators or scrubbers in coal power plants. And this led to a dramatic reduction in the amount of sulfur dioxide in the atmosphere, which in turn led to the air becoming clear. Once the air became clear again, it warmed up. And it's been warming up at an increasing rate ever since.